Hello and welcome to Lives of Water Part 2, the second in a series of videos on water and creative cartography, hosted by Jakmel Ekspresyon. My name is Trevor Even, and this project is brought to you thanks to collaboration between myself, Professor Carly Trott at the University of Cincinnati, Sue Frame, Jean-Pierre Peterson, and Stanley Bichara at Jakmel Ekspresyon. Our goal in this series covers three main areas that have emerged as being important based on discussions we've had as a team and courses that have been offered over the last several years, focusing on local water issues, community mapping, and the challenges of community water management in Jacmel. Today, we're going to be focusing on the ideas and tools we will need in order to understand how to take our knowledge of water systems and work to explore the spatial approach to addressing major problems in our communities. We're also hopefully going to get started with playing around with some of the tools we will use in future work and learning about how to take our efforts from ideas to execution. Because what we need to understand in order to engage with the work of mapping water data and thereby changing the ways we manage and access water requires first that we understand the overall approach to mapping and data work that informs contemporary approaches to the problem. That way, when we want to map something, whether it is about water or related systems, we have everything we need to get going. For this reason, today's video is broken down to three main topics. First, we're going to talk about spatial data and what it means to think spatially. Second, we'll talk about GIS systems, what they are and how they work. And third, some GIS tools that we can use to make our analyses and cartography work happen. Put another way, the reason that we need all of these different tools to make plans and find solutions to water problems is that the systems that bring water to us are grand and complex. More importantly, they connect to nearly every aspect of our lives, our environments, and the things that we care about. And, as we learned in the last class, since water systems can be affected by activity taking place at any part of the watershed, we need a way to step back from what is right in front of us to get a sense of the bigger picture of the whole basin. The question is then, how do we step back in such a way as to be able to incorporate the various different kinds of knowledge that we'll need in order to engage with water systems in a meaningful way? That is, how do we gather information, analyze it, and develop the conclusions we need in order to act in an intelligent manner? Part of the answer to this question, I think, lies in what is known to geographers as the spatial approach. All relationships have a spatial element, after all. Everything is related to things by their relative position in space. Life systems, likewise, are characterized by their distribution across space and the underlying physical components of that space. Hazards, then, arise from patterns of relationships. We always want to know where hazards occur, if only to walk away. Complex systems, in turn, are unified through their spatial relationships. Individuals, families, businesses, economies, hydrology, plants, animals, transportation infrastructure, and the movements of all things can theoretically be characterized in a spatial array relative to a fixed reference scheme. And so that is why, really, the spatial approach is really at its core about building data sets with a reference to their location in space and, in some cases, in time. What makes the spatial approach possible for us, however, is the rapid advancement of technologies related to gathering, preparing, and sharing information about the Earth and the composition of the innumerable processes taking place upon it. Whether that's you and me using cables buried under the ocean to talk about maps in water, that is the internet, or the vast forests of the earth and all the trees in them growing and breathing each year within the shifts of the seasons. What makes our access to this possible, then, is spatial data, or data that has been referenced to a coordinate system corresponding to its location on the land, ocean, and inhabitants of the earth. That is, their configuration of space, their activities on Earth and underneath it, as well as above the Earth's surface. A million eyes, some capable of seeing far beyond what we can, have opened in the sky above us, And with the right skills, we can give our communities the possibility to see through those eyes. This is the value of spatial data. But what is data, beyond something that always seems to run out on your phone? A common dictionary definition is that data is a unit of facts and derived statistics from observable phenomena collected together for reference or analysis. We could also think of it as information generated by us through technological or cultural means, like taking a picture or filling out a survey, that are organized in a systematic way so that they can be analyzed to generate insights about broad social or physical processes and transformations. Now, data can fall into any number of categories as to its particular relevance. Transportation data tells us how many cars and motos move through a road. Natural data could be the types of trees and their abundance or process of disappearance over time. It could be how much money is spent at different stores in a town, or a measure of the overall health of the economy. But whatever type of data it is important that it is organized so that many people can look at it, and so that many different sources can generate it so that it all fits together as one bundle of understandable knowledge. To put it even more simply, data is when we have a sense and record that moment of awareness in a way that lets us put it in a package so that others can take part in our experience of the world, so that we can teach and learn and change as communities. Spatial data is when we use scientific tools to sense the world and record the position of those observations in time and space. To do this, we make reference to systems of known coordinates, such as longitude and latitude. This tells us where something is when it was interesting enough for us to make note of it. There are other systems of spatial reference, some of which we will probably encounter by the time we're done with the class. But the details are not as important as the understanding that you must know what the spatial reference is in order for spatial data to work. It is about where things are in space. Now, spatial data can take on many forms, as the things we might want to know about inhabit space in different ways. Unique places have a roughly singular location, or an area that they cover. Things like the population of a place, however, moves around throughout the day. More importantly, there can be lots of living things in the same place over a given amount of time. It can't just be a bunch of points that you're thinking about. Instead, you need a way to depict a quantity within an area, even if that area is as small as a square acre or a house. On the other hand, things like roads can be characterized both by their location and by how they intersect with one another. The network of those roads is what is important to their function, as much as the location of any given point on a road. That is why things like roads, power lines, water lines, and other interconnected systems need to know both where they are and how they are connected relative to one another. If you are planning a set of buildings, on the other hand, you want to know data that has more detail. You'd want to know how the ground slopes across the area, where water flows in pools, and what kind of soil you are building on. These kinds of data are not simply here or there. They are gradient in nature and can vary subtly or dramatically across the space that you are interested in. That is why when we work with spatial data, we have to remember that we are working with what is usually many different types of data. The first type of data that we might want to think about is something we often encounter every day, which is categorical or nominal data, which is data that is organized into two or more categories that have no specific order or hierarchy. This is things like, for example, names, types of buildings, addresses, department names in a school, or cultural groupings. Again, these are things that are simply unique identifiers that we may want to know about, but that don't have some set relationship with one another. The second type we want to think about is ordinal data, which is data that is categorized into two or more categories that have a clear order to them. This is things like low, medium, and high rankings that come about as a result of an analysis, or grades that you get in school, where one grade is better than the other. The last type of data that we might want to think about is numeric data. Numeric data is data that's in the format of a number within a measurable range with reference to a specific unit of measurement. Examples here are things like height and weight, distance, speed, or, or area. In GIS work, elevation is almost always used as a background layer and is an example of a numerical variable that is continuous across the surface in question, as we'll see in a minute. For example, this map shows roadways and trails within and around Jacmel. It was sourced from OpenStreetMap, a nonprofit project that relies on community members to manually create features within a shared global database. Here, lines are used to represent roadway segments and connections, with each entry in the database having information on the road's position, its length, the vertices that define it, and its name, type, and other characteristics. This means the data file associated with this roadway layer contains several types of categorical, ordinal, and numerical data, all within the same geographically referenced spreadsheet. Similarly, these shapes show building outlines, also from OpenStreetMap, for the central Jacmel area. These buildings are, much like roadways, symbolized as collections of connected lines, or polygons, whose information is a combination of different numerical, geographic, and categorical information, like the name of the building, if it has one. Both the roadways and building outline feature layers are what is known in GIS work as vector data, which is data organized as geometric objects of a given dimension. This can include point features with only one precise location, line data, such as for roads or borders, or polygon data, which depicts an area of space. In all cases, these types of data points are stored in a spreadsheet format that includes both their important characteristics as well as their geometric configuration in space. In general, vector data is anything you can draw on a map with a pencil and is usually easier to work with and conceptualize, as it is most often corresponds to clearly identifiable things that we interact with in the real world that are definitely either present or not. But not all of the things that we need to understand are so simple. In fact, some of the most important aspects that shape our lives at the scale of watersheds and basins are not just one single feature or set of features, but are a continuous surface of subtle changes and relationships that cover wide areas. For example, in this map, we see a depiction of elevation above sea level for the area within and around the greater Jacmel River Basin. In this view, the bright yellow areas represent the highest elevation points, the mountain peaks and ridge lines that contain the basin. The darker areas in purple and gray show relatively lower elevation areas. Together, they give us a picture of the total surface of the land and allow us to understand how the topography creates distinct lines of flow for water falling as rain, which here are shown in blue. This kind of data can't just be depicted as simple shapes, even if we have millions of shapes, but instead must exist as a continuous surface, sort of like a big sheet pulled over the entire department. This type of data set is referred to as a raster data set, or matrix data set. Instead of being composed of a table of shapes with attributes, it is comprised of specifically sized cells arrayed in a grid formation that ultimately become the pixels depicted on our screen. In general, we use raster data when we want to describe an area in terms of all of the characteristics of interest within it, and not just a specific set of features. So for things like climate information, which take place everywhere, or elevation, which is a characteristic of every piece of land, or soil quality, which has relevance everywhere, we use raster data sets. Rasters can be thematic, or a series of categories such as different types of land use or soil quality. They can be continuous, numerical variables such as elevation, average temperature, or rainfall. They can also just be imagery, that is, photographs of different types that give us a bird's eye view of the terrain. In all cases, however, they are ultimately built around a matrix of pixels carrying information that is relevant to us as viewers and analysts. An important thing to remember about rasters, however, is that they are always something of an illusion. That is, just like photographs or paintings, they are ultimately images made up of individual units of information. In the case of rasters, this is the individual pixels that carry information within the raster dataset. For example, take this high-resolution imagery gathered by the Haitian government of Jacmel using cameras housed in small airplanes that flew over the city in 2018. At this level of zoom, it looks like any other photograph. However, as we zoom in, we begin to see that it is actually just a collection of differently colored pixels, which, when put together as a whole, gives us an image our brains can resolve and understand. This happens because our eyes really only see three colors: red, blue, and green. And our brain takes these signals and processes them to produce the full range of colors that we experience. As a result, photorealistic images appear on our screens and phones based on technology that only produces a few differently coded color signals. Spatial data derived from satellites, which have cameras and other equipment that can detect a wider range of radiation from the Earth's surface and atmosphere, are able to create images that contain information that we would not normally be able to see, such as ultraviolet light, X-ray radiation, or infrared light. We won't be dealing with anything like that's so complicated in this class, but if you start to explore satellite data from NASA or other agencies in the future, this is important to bear in mind. The raster dataset we are going to use in this class as a cool looking background layer is also another great example of how technology is increasingly allowing us to see things we normally wouldn't be able to see. Specifically, it is derived from what is called LiDAR, or Laser Imaging Detection and Ranging. This works by flying a plane with a low-power laser emitter over the area of interest and recording the differences in time that it takes for a beam of light to bounce off of the ground surface and back to a detector on the plane. By analyzing these changes in the time it takes the light beam to travel, you can get a highly accurate idea of the elevation of every square inch or so of a vast landscape. For our data set, for example, we have pixels that are just a half a meter wide, or roughly as wide as an average person's shoulders. That means we get a very realistic idea of what the contours of the landscape are, and the vivid texture of the basin's volcanic landscape. To summarize, raster data is data arrayed in a continuous matrix across the area of interest. It depicts features like average air temperature, average precipitation, elevation, slope, or geology that can be attributed to every area within the dataset. In this way, they are similar in character to artworks that use pointillism, hyperrealism, or simply photography, and that they are basically sensing the world as it is and copying that sense into an organized format. Vector data is data that is composed of discrete points, lines, or shapes that symbolize real-world features. In this way, it is equivalent to artwork that utilizes line drawing, such as comic books, abstract art, or cartoons, works that utilize symbols to represent aspects of the real world that we can readily observe. The real world, on the other hand, is always beyond these types of data sets, no matter how detailed they might seem. Just like the most detailed painting or high-resolution photo is only a glimpse of the real world, spatial datasets only give us a recording of reality at specific points in time, and they are always constrained by the tools we use to create them and the ideas about our observations that we brought to the data creation process. In a more practical sense, what is important is that you need to make sure you are using the right tools within GIS programs when we are working with different types of data sets. Turning our attention back to water, we can start to see how spatial data about water quality might be gathered and analyzed using the spatial approach. As we discussed in the last class, a number of different questions come to mind when we want to talk about water quality concerns. At the simplest level, we want to understand the most basic question of whether or not water is safe to consume and use for our specific purposes. Since almost all water is, of course, contaminated in some way, we might also want to know how to deal with that contamination by treating it with chemical or physical means. To do that, of course, we need to know what kind of contamination is present and how contaminated the water might be. In turn, we also have to understand what the sources of water contamination might be so that we know how to deal with contamination problems over the long term by figuring out what steps we can take to reduce that type of contamination in the future. In all of these cases, we will use different real-world tools to help us. Water tests that tell us the presence of different chemicals or other pollutants, for example, can be used to help us with many of these problems. We can take photographs and make field observations about surrounding land use and other factors that might be impacting water quality locally. We might explore areas upstream of a water site to understand how contamination there might be washing downhill and affecting our chosen water site. What spatial data about water and mapping water data then allows us to do is to put these kinds of information, chemical tests, site observations, patterns, into an organized system so that we can understand the patterns of contamination that occur in our area and potentially address the major causes of water quality impairment that affect our lives. Another type of data that is of critical importance to making sustainable decisions is hydrological data, or data that tells us about where, when, and in what quantities water resources move across the landscape. This includes information on where water is located, where it pools and flows, as well as information about how much water is moving from place to place. By examining this type of information over time, we can begin to understand the patterns in water availability that we can expect in the future, as well as how changing weather patterns, which are the ultimate source of water resources, may affect our ability to access water in a reliable way. Hydrological data can also tell us important information about how heavy rainfall events or other types of sudden water movement can affect our well-being. For instance, whether or not a given storm will result in flooding that damages our lands, homes, and potentially our lives. Thanks to some rather admirable effort from some of the students at JE, we have some very interesting data to work with as a class that looks at water quality issues in a number of ways across a wide range of sites from around Jacmel and the surrounding Jacmel Basin. These include basic water tests for bacterial contamination, more complex tests for an array of chemical contaminants, and on-the-ground observations of water use sites for different activities like cooking, washing, livestock activity, and industry that all might affect water quality. This map shows hexagons for all the different sites that have been visited for data collection over the last couple of years, and where we have information that can help us to tell the story of the many lives of water taking place in the Jacmel area. To manage spatial data and other interesting information we hope to map out, we need to organize it in a systematic way. To do this, we create what is called a Geographic Information System, or GIS. Put simply, a GIS is a framework for gathering, managing, and analyzing data that associates all of our various data points with a shared spatial reference. This lets us determine patterns, notice changes over time, and visualize our data in increasingly exciting ways. It is a collection, ultimately, of different data layers, often including both rasters and vectors of different types that, when put together, allow us to perform interesting analyses and to visualize information at multiple different scales. In order to create and manage GIS, we need the right tools. Over the last few years, luckily, there's been some incredible advancement in the availability of GIS toolsets that are free for public use. The most important of these is Quantum GIS, or simply QGIS, which is an open source, collaborative, and non-profit GIS system used by millions of professionals and amateur geographers around the world. Perhaps most importantly, QGIS is far and away one of the best tools available for making stunning and visually exciting maps of our data. We will have a chance to work with some of these options as we go forward, but for now, if you want to get a head start, you can begin playing around with the program. There are also a large number of tutorials and training videos available in French or English on YouTube that have been created by members of the QGIS user community if you are interested in learning more on your own. Just search for QGIS tutorial and you'll find everything you need. When we're working with QGIS, though, we need to be thinking about where our data lives. That is, where it is stored, as that will have a lot of impacts on the performance of our computers and whether or not we need internet to be working in order to get our mapping effort underway. This is because local data, or data that is stored on the computer hard drive, is only one kind of data set that can be used for GIS work. Local data can be downloaded from trusted sources or created as needed. If we create it ourselves, however, it should be organized in an easy to understand way so that other people can use it and make sense of what it is. Ideally, all of our local data is stored on the same hard drive and in a database configuration so that your computer doesn't have to activate multiple data channels simultaneously when accessing multiple layers. The reason we have to care about this is because GIS files can be extremely large. So large, in fact, that they may fill up your whole hard drive. You always need to check to ensure you have the bandwidth and storage space you need before you download data from government sources or other trusted sites. For local data, vector data is often in the form of a file called a shape file, which is usually a set of files in a zipped archive. It may also be in the form of Esri feature classes in a geodatabase, or in a Google Earth KMZ or KML file. QGIS can also handle simple text tables of data as long as you are able to identify the spatial reference coordinates. Raster data types have a lot of different names, with GeoTIFF and image being the most common. But because they are generally much more detailed than vector data sets, rasters are almost always larger in file size. Service, or cloud data, is another form of data set that we can use in GIS work. It is data that is stored on the internet, usually in government or corporate servers, that we access on an as-needed basis. It can take the form of both raw data that we can access directly and modify and visualize, as well as in the form of images of that data, like a screenshot, that is smaller in size to download, but that is limited in how it can be manipulated. In both cases, you need the internet to be up and working in order to access these types of layers. They can come in the form of web map services, web feature services, Google's proprietary services KML and KMZ, ArcGIS map and feature services, or as simple XYZ tiles that work like images. Whatever the case, we need to make sure that we have the bandwidth and the stability necessary to access these forms of datasets reliably if we're going to depend on them for our projects. In preparation for this class, I've put together a number of interesting datasets that you should have access to locally. These include the digital elevation model you've seen visualized in some of the Jacmel basin maps, as well as hydrologic datasets I developed using this data. We also have some high-resolution aerial photograph imagery from the Haitian government to work with, in case you want to find your house or something. Thanks to the OpenStreetMap organization, we also have things like roadways, building outlines, and some other interesting data that we can use to make useful and recognizable maps of our area. Finally, we have our water sampling and observation data sets, which were made possible by the hard work of the students and volunteers at JE. All of these are available to you to start exploring as we get into the actual work of learning how to handle QGIS. Of course, you aren't limited to just the data that I have put together. The range of data sets available to you is growing every day, with multiple valuable sources of global data being available for download. Some key resources include the NASA Earth Observatory portal, which includes some very interesting satellite imagery and other data at the global scale. The Esri Open Data Hub is a source for global data sets and data services that can be used to find out a wide array of physical, social, and other information about countries all over the world. Natural Earth is a global nonprofit that provides data sets focusing on natural features of the globe at different resolutions and level of detail. And OpenStreetMap, which we've mentioned before, can also be an excellent source for base map layers and other data sets that help put your data in context for viewers. The USGS Earth Explorer also gives global users access to data sets on all manner of information, mainly focusing on the Americas and Caribbean. Data specific to Haiti is also becoming more and more reliable and sophisticated, with the best source I have been able to find being haitidata.org. Here you can find imagery, government boundaries, hazard exposure layers, and all sorts of information that have been provided for public use by the Haitian government and researchers working in Haiti. So then, that was a lot of information to process, no doubt, and we still have a ways to go. But as we think about what we've learned here today, let's consider some of the types of data we might have heard about when we hear about Haiti and Jacmel. What kinds of data have you heard about that you might want to study and map out? What questions do you have about your area that you wish you had clear, spatially explicit answers to? Let's also investigate a bit. What kinds of data can we find when we search through different sources on the internet? Do you see anything that is missing that you would like to see or maybe even build yourselves? And finally, let's prepare. In our next class, we are going to go into more detail on what the work of creating compelling maps looks like. But for now, we need to get familiar with QGIS and how it works. Let's spend some time today playing around with the program, looking at different types of plugins and what they can do, and starting to build some basic maps from the datasets you have available to you. Don't worry if it seems overwhelming, as we will be here to help you along. So that's it. Thank you, and see you in the next video.